The universe is a cosmic ledger that does not balance. For all the stars, galaxies, and light we see, the accounting comes up catastrophically short. Imagine checking your bank statement to find that over 95% of your money is simply labeled unknown. That is the staggering situation facing cosmology today. The universe is mostly made of missing energy, two mysterious entities called dark matter and dark energy that dictate the fate of everything, yet we cannot see or touch them. By the end of this exploration, you will have a front row seat to 30 of the most brilliant and bizarre theories attempting to solve this ultimate cosmic mystery. We will venture from Einstein's greatest blunder to the possibility that our entire reality is a hologram, from phantom forces that could rip atoms apart to the controversial idea that we live in just one of infinite universes. What does it mean that the cosmos is dominated by shadows we do not understand? The journey to find out begins now. What do you think is the strangest possibility hiding in the dark? This missing energy crisis finds its roots in a single number, a correction factor added and then abandoned by the greatest scientific mind of the 20th century. Albert Einstein, while crafting his theory of general relativity, faced a problem. His beautiful equations predicted a dynamic universe, one that must either be expanding or contracting. Yet the scientific consensus of his time, including his own belief, held that the cosmos was eternal and static. To force his equations into alignment with this static model, Einstein introduced a fudge factor, a mathematical term he called the cosmological constant. It represented a repulsive force, a kind of anti-gravity woven into the fabric of space itself, perfectly balanced against the pull of matter to keep everything still. When Edwin Hubble later discovered the universe was indeed expanding, Einstein famously called the cosmological constant his greatest blunder and removed it from his equations. The story, however, was far from over. Decades later, when astronomers confirmed the expansion was not just continuing but accelerating, that discarded idea made a triumphant and shocking return. The cosmological constant is now the leading, simplest candidate for dark energy. It proposes that empty space is not nothing. Instead, the vacuum of space possesses a fundamental, immutable energy density. This energy acts as a constant push, a gentle pressure inherent to the cosmos that causes the expansion to speed up over time. The mathematics are elegantly simple, a single number that fits the observational data remarkably well. Yet this simplicity masks a profound and unsettling mystery. When physicists attempt to calculate what the value of this vacuum energy should be using our best theories of quantum mechanics, they get an answer that is wrong by a factor of 1 followed by 120 zeros. It is the worst theoretical prediction in the history of science. This staggering discrepancy means we are either missing something fundamental about how gravity and quantum physics interact, or the cosmological constant is not the final answer. Its revival solved one cosmic riddle, only to birth an even deeper one about the very nature of nothingness. That single, stubborn number of the cosmological constant feels too perfect, too rigid for a universe built on change. What if dark energy is not a fixed feature of empty space, but something alive, something that evolves? This brings us to our second theory, a concept with a name fit for ancient myth: quintessence. In medieval cosmology, quintessence was the fifth element, the pure substance of the heavens beyond earth, air, fire, and water. In modern physics, it proposes that dark energy is a dynamic field, a kind of cosmic weather that permeates all of space. Unlike the static push of the cosmological constant, quintessence is a fifth fundamental force, one that has a strength and an effect that can change over both time and distance. Imagine it not as a uniform background hum, but as a gentle, invisible wind blowing through the cosmos, a wind whose direction and speed might subtly shift. Physicists model this using something called a scalar field, a mathematical description of a value that can differ from point to point in space. Picture a vast, gently sloping hillside covered in a layer of mist. That mist is the quintessence field. As it rolls down the slope of its own potential energy, its behavior, its density changes. This rolling could have started slowly, explaining why the universe's expansion was decelerating in its youth under gravity's dominance, only to have quintessence's repulsive push gradually take over and cause the acceleration we see today. This dynamism offers a potential solution to the coincidence problem, the puzzling fact that we live in the brief cosmic epoch where dark energy and matter have comparable influences. With quintessence, it is not a bizarre coincidence, it is just a phase we are passing through in the field's long evolution. The future it paints is far more dramatic than the steady acceleration of a cosmological constant. If the quintessence field grows stronger over time, it could lead to a truly apocalyptic finale known as the Big Rip. In this scenario, the repulsive force of dark energy would not just push galaxies apart, but would intensify until it overcomes the forces holding galaxies, then solar systems, then planets, and finally atoms themselves together, shredding the fabric of reality. Conversely, the field could eventually decay or reverse, causing the acceleration to slow, stop, or even pull the universe back together in a dramatic big crunch. Quintessence transforms dark energy from a cosmic constant into a character in the universe's story, one with a past and a fate that remains utterly unknown. Perhaps the shadows we are chasing are not made of matter at all. What if the problem lies not in the missing pieces of the universe, but in the very glue that holds it together? This is the radical proposition of the third theory, modified Newtonian dynamics, or MUND. Instead of inventing a new, invisible substance to explain the motions of galaxies, MUND suggests we have simply misunderstood gravity itself on the largest scales. The story begins in the early 1980s with physicist Mordechai Milgrom, who was troubled by the galaxy rotation problem. Stars at the outer edges of spiral galaxies were moving far too fast to be held by the visible mass according to Newton's laws. Rather than accepting the need for a halo of dark matter, Milgrom asked a different question. What if gravity does not behave as we expect when its pull becomes incredibly weak? He proposed a simple but revolutionary tweak. Newton's famous law that force equals mass times acceleration might only be an approximation that works well here in our solar system. But in the extreme outskirts of a galaxy, where the gravitational acceleration drops below a certain tiny threshold, the rules change. Milgrom formulated an empirical adjustment, a new mathematical relationship where gravity falls off more slowly with distance in these low acceleration environments. The result was astonishing. When you applied this single modification, the predicted rotation curves of galaxies matched the observed data almost perfectly without invoking a single particle of dark matter. The stars were moving exactly as fast as they should according to this revised gravity. It was an elegant solution that cut the Gordian knot. MUND's success is not just theoretical. It has consistently predicted the motions within many types of galaxies with remarkable accuracy, often outperforming standard dark matter models for individual galactic systems. It feels like a cleaner, more direct explanation for the specific anomaly that started this whole mystery. Yet for all its beauty, MUND faces a universe of complications. Its first major hurdle is galaxy clusters. When we look at these massive gatherings of hundreds of galaxies, the visible matter alone cannot account for the immense gravitational lensing we see, where the cluster's gravity bends light from objects behind it. Even with MUND-modified gravity, there still seems to be a significant amount of missing mass in these colossal structures. Some proponents suggest there might be ordinary, hot gas we have not fully accounted for, but the gap remains a serious challenge. The second, and perhaps more damning, obstacle is the cosmic microwave background, the ancient afterglow of the Big Bang. The intricate patterns in this radiation are a precise blueprint for the early universe, and they strongly indicate that ordinary matter alone could not have clumped together to form the galaxies we see without the gravitational scaffolding provided by dark matter. The standard model of cosmology, with its dark matter and dark energy, reproduces this blueprint with incredible fidelity. To date, no modification of gravity alone has been able to fully replicate this success without reintroducing some additional, unseen component. So we are left with a fascinating standoff. Does man reveal a profound truth about gravity that we have been blind to, forcing us to rewrite the laws of physics? Or is it a brilliant but ultimately incomplete description, a local fix that cannot explain the cosmos as a whole? The theory forces us to confront a fundamental choice. Are we missing matter, or are we missing the point? The standoff between missing matter and modified gravity presents a stark either-or choice, but what if the answer is neither? This leads us to a more unified and perhaps more elegant possibility. Theory 4 proposes that dark matter and dark energy are not two separate puzzles, but two different faces of a single shadowy entity. Imagine a cosmic chameleon, a fluid so exotic that its properties transform over the lifetime of the universe. In the dense, crowded conditions just after the Big Bang, this fluid clumps together under gravity, acting exactly like the invisible scaffolding of dark matter, pulling galaxies into shape. Then, as the universe expands and thins out, this same fluid undergoes a phase change, becoming smooth, repulsive, and dominant, driving the accelerated expansion we attribute to dark energy. One substance, two cosmic roles. This is the vision of a unified dark fluid, and its most famous candidate is known as the Chaplygin gas. The name comes from a century-old model in aerodynamics, but its application to cosmology is profoundly strange. The Chaplygin gas is defined by a specific and unusual equation of state, a mathematical rule linking its pressure and density. In the early universe, when its density is extremely high, the pressure becomes negligible. This makes it behave like a pressureless cold dust, which is exactly how we model dark matter. It gathers in halos, providing the gravitational glue for galaxies. But as the universe expands and the density of this gas drops, its negative pressure begins to assert itself. It transitions smoothly from acting like attractive matter to acting like repulsive energy, mimicking a cosmological constant. The elegance is breathtaking. With one theoretical ingredient, you solve both of the universe's biggest mysteries. You get the structure formation of the early universe and the accelerated expansion of the modern universe from a single, evolving source. It is a beautifully parsimonious idea, cutting the unknown components of the cosmos in half. Yet for all its conceptual appeal, the Chaplygin gas model has run into serious trouble with reality. Observations have placed it under immense strain. The way this unified fluid would suppress the growth of cosmic structure, the very galaxies and clusters we see, does not match what our telescopes reveal. The universe appears to need dark matter that clumps aggressively and independently early on, and dark energy that remains smooth and dominant much later. The Chaplygin gas, trying to be both, struggles to satisfy the detailed timeline written in the stars. While specific models like the Chaplygin gas have fallen out of favor, the core idea of a unified dark sector remains a tantalizing thread for theorists. It suggests that our categorization of the cosmos into distinct boxes might be a human limitation, not a cosmic truth. Perhaps in the darkness there are not two monsters, but one with a shape we cannot yet comprehend. The most terrifying fate for our universe may not be a slow fade into darkness, but a sudden, violent end written into the fabric of space itself. This is the domain of phantom energy, the darkest and most extreme incarnation of dark energy we can conceive. While the cosmological constant has a fixed, gentle push and quintessence might ebb and flow, phantom energy is something else entirely. It is defined by a single, monstrous property. In the equations cosmologists use, there is a value called W, the equation of state, which describes the relationship between the pressure and density of a cosmic component. For the cosmological constant, W equals exactly -1. For phantom energy, W is less than -1. Its pressure is not just negative, it is more negative than the vacuum itself. This seemingly small mathematical tweak has apocalyptic consequences because it means the energy density of this phantom field does not remain constant or slowly change. It increases as the universe expands. The density of phantom energy grows, which makes the expansion accelerate even faster, which in turn makes the density grow again. This creates a runaway feedback loop of repulsive gravity. The result is a cosmological doomsday with a precise expiration date known as the Big Rip. Imagine the acceleration of the universe not as a steady pressure, but as a force that strengthens exponentially with time. Billions of years from now, long after the last stars have died, this phantom force would first overcome the gravitational glue holding galaxy clusters together. They would fly apart. Then, as the phantom density soars, it would target individual galaxies. The Milky Way would be shredded, its stars scattered into the endless void. The horror would come closer to home. As the repulsion continued to amplify, it would eventually surpass the force holding our solar system together. Planets would be ripped from their orbits. Then, as the final moments approached, the phantom force would exceed the electromagnetic forces binding matter. In the last minutes or even seconds before the end, Earth itself would be torn apart. Mountains, rocks, and finally individual atoms and atomic nuclei would be violently disassembled. In a finite time, the expansion rate would mathematically become infinite, and the fabric of space-time itself would be torn asunder. It is a finale of absolute, unimaginable destruction. Yet for all its dramatic power, phantom energy faces severe theoretical hurdles. The primary issue is one of quantum instability. In quantum field theory, a phantom field with its W less than -1 would have a negative kinetic energy. This essentially means it has a ghostly quality. Such a field is notoriously unstable, prone to runaway fluctuations that could spawn infinite amounts of particles and energy from nothing, violating fundamental physical principles. It could make the vacuum of space unstable on microscopic scales, potentially causing the universe to decay instantly into a catastrophic new state. Most physicists view phantom energy as a mathematical possibility within certain models, but not a likely physical reality. It serves as a stark boundary, a warning of what the most extreme form of dark energy could entail. It forces us to ask, is our universe on a gentle cruise into emptiness, or is it, against all odds, riding a phantom wave toward a definitive and violent end? Phantom energy threatens to tear reality apart from the inside, but another theory suggests the problem is even more fundamental. What if our entire three-dimensional universe, with all its galaxies and dark energy, is merely a projection, a cosmic illusion painted on a distant two-dimensional surface? This is the staggering claim of the holographic principle, and it may hold the key to why dark energy exists at all. The idea did not begin with cosmology. It emerged from the fiery depths of black hole physics. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, a measure of its hidden information, is not proportional to its volume, but to the surface area of its event horizon. This was bizarre. In our everyday world, the information content of a system, like the data on your computer, scales with its volume. But for a black hole, the ultimate information sink, all the data about what fell in is somehow encoded on its spherical surface. Decades later, string theorists like Leonard Susskind and Gerard T. Hooft took this radical notion and proposed a principle. Perhaps this is not just a quirk of black holes, but a fundamental law of the universe. The holographic principle states that all the information contained within any volume of space can be fully described by physics operating on the boundary of that region. Imagine you're watching a breathtakingly realistic three-dimensional movie. Every detail, every star, every person seems to have depth and substance. Yet all that information, the entire three-dimensional experience, is encoded on a flat, two-dimensional screen. According to the holographic principle, our universe might be like that movie. The three-dimensional cosmos we perceive, with its trillions of galaxies, could be a holographic projection from a vast, two-dimensional shell that surrounds us at the edge of the observable universe. This is not science fiction, but a serious framework for unifying quantum mechanics and gravity. Now enter Raphael Bauso and other cosmologists who asked a profound question. If our universe is holographic, what does that imply for the vacuum energy, for dark energy? Their work leads to a startling possibility. In a holographic universe, there is a natural limit to how much information, and therefore how much energy, can be contained within a given volume. You cannot pack more information into a region than can be encoded on its surface. This cosmic data limit imposes a maximum allowable value for the energy density of the vacuum. Think of it like a cosmic hard drive. Our three-dimensional universe is the stored data, but the two-dimensional boundary is the hard drive's surface. There is only so much storage space. The vacuum energy, the dark energy that fills empty space, is like a background file taking up some of that precious storage. The holographic bound says this file cannot be infinitely large. In fact, when physicists calculate this maximum using the observed size of our universe, the number they get is intriguingly close to the tiny but non-zero value we actually measure for dark energy. It is not a perfect match, and the calculations are fiercely complex, but the direction is compelling. The holographic principle does not generate a specific number for dark energy from first principles, but it provides a powerful ceiling, a reason why the vacuum energy is not the colossal, universe-shattering value predicted by naive quantum field theory, but is instead the faint, persistent whisper we observe. It suggests that dark energy is not some arbitrary ingredient added to the cosmos. Instead, its existence and its specific, small value could be a necessary consequence of a deeper truth, that our universe is, at its most fundamental level, an information structure. The darkness we cannot see may be the shadow cast by the limits of cosmic information, written on the boundary of everything we know. The holographic principle offers a cosmic data limit, but to understand why that limit is so desperately needed, we must confront the single most embarrassing failure in modern physics. It is known as the vacuum catastrophe, and its numbers are so vast they defy human intuition. This catastrophe begins with a beautiful and fundamental idea from quantum mechanics: zero-point energy. Even in a perfect vacuum at absolute zero temperature, empty space is not truly empty. According to quantum theory, the vacuum is a seething, bubbling sea of virtual particles. Particle-antiparticle pairs constantly wink into and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This perpetual quantum jitter means that every cubic centimeter of so-called empty space possesses a baseline, irreducible energy. This is the zero-point energy of the quantum vacuum. Now, if this energy is real, and general relativity tells us that all energy curves space-time, then this vacuum energy should act as a cosmological constant. It should contribute to the expansion of the universe, so physicists did what seemed logical. They took their incredibly successful theory of quantum field theory and attempted to calculate the total zero-point energy density of the vacuum. They summed up the contributions from every possible quantum fluctuation, from every field across all possible wavelengths. The result was not just wrong. It was catastrophically, monumentally wrong. The theoretical prediction for the vacuum energy density came out to be a number roughly 1 followed by 120 zeros larger than the actual observed value of dark energy we measure in our cosmos. To put that incomprehensible discrepancy into perspective, it is the difference between the energy contained in a single proton and the energy contained in the entire observable universe. It is the worst prediction in the history of science. This means our two most powerful theories, quantum mechanics and general relativity, when asked a simple question about the energy of nothing, produce an answer that is off by a factor of 10 to the 120th power. The vacuum catastrophe is not a minor rounding error. It is a screaming siren that our understanding of fundamental physics is profoundly incomplete. This staggering failure is the primary engine driving theorists to propose radical solutions like the holographic principle or supersymmetry. Supersymmetry, for instance, is an elegant theoretical framework that posits every known particle has a hidden superpartner particle. One of its beautiful mathematical consequences is that the contributions of these partner particles to the zero-point energy would perfectly cancel out the contributions of the ordinary particles, potentially driving the net vacuum energy down to zero or a very small value. Yet, despite decades of searching, no evidence for these superpartners has been found. The vacuum catastrophe remains, a haunting reminder that the dark energy we see might be just the faintest ghost of a theoretical energy so colossal it should have torn the universe apart in its first instant. Why is the cosmos so eerily quiet when our equations scream of infinite noise? The vacuum catastrophe screams for a revolution, not just a revision. What if gravity itself is an illusion, a side effect of something far more fundamental? This radical idea forms the heart of Theory 8, emergent gravity, pioneered by theoretical physicist Eric Verland. His proposal is as elegant as it is mind-bending. He suggests that gravity is not a fundamental force of nature like electromagnetism. Instead, gravity emerges much like temperature or pressure emerges from the collective motion of countless molecules. You cannot point to a single molecule and ask for its temperature. Temperature is a collective property. Verland argues gravity is the same. It is a thermodynamic force that arises from the quantum entanglement of the microscopic building blocks of spacetime, a consequence of information and entropy. To understand this, picture the universe as a vast cosmic hologram made of unimaginably tiny bits of information. These bits are entangled, connected in a complex web. When you place a mass like a galaxy into this informational fabric, it disrupts the entanglement in its vicinity. The fabric responds elastically, trying to restore its informational equilibrium. This elastic response, this push back against the disruption, is what we perceive as gravity. It is not a force pulling things together, but a thermodynamic gradient like air rushing to fill a vacuum. Now, here is where dark matter enters the picture. In Verland's framework, the phenomena we attribute to invisible dark matter halos around galaxies are not caused by unseen particles at all. They are the natural, elastic response of this emergent spacetime to the presence of the visible, baryonic matter we can see. The extra gravitational pull felt by stars at the edges of galaxies is not from extra mass. It is from the way the galaxy's mass has altered the entanglement structure of space itself, creating an additional gravitational effect that mimics the presence of dark matter. The theory makes specific, testable predictions. For instance, it suggests a tight relationship between the amount of visible matter in a galaxy and the apparent dark matter effect. In some cases, like low surface brightness galaxies, emergent gravity's predictions match observations remarkably well without any free parameters. It offers a beautifully parsimonious explanation, removing the need for a mysterious particle we have never detected. Yet, like all revolutions, it faces fierce challenges. The theory is still under development, and its predictions for the largest scales, like galaxy clusters and the cosmic microwave background, are not yet fully worked out. Some early tests against gravitational lensing data have been mixed, with the standard dark matter model often providing a better fit to the intricate bending of light around massive clusters. Verlin's work is not a finished theory but a profound research program, a call to rethink the bedrock of physics. It asks us to consider that the missing energy of the universe might not be missing at all. It might be a phantom in our equations, a sign that we have been mistaking an emergent effect for a fundamental ingredient. The darkness could be the shadow of our own misunderstanding, cast by the deep, informational nature of reality itself. Emergent gravity suggests the missing piece is in our understanding, but what if the answer lies not in our universe but outside of it? This leads us to one of the most profound and contentious ideas in modern cosmology, the multiverse and the anthropic principle. It proposes that dark energy's bafflingly small value is not dictated by a beautiful, singular law of physics. Instead, it is a cosmic accident, a random lottery ticket drawn in a reality of infinite possibilities. The stage for this idea is set by string theory, the leading candidate for a theory of everything. String theory's mathematics do not yield one unique universe. They describe a vast, perhaps infinite, landscape of possible universes, each with its own unique set of physical constants, its own version of the laws of nature. In this cosmic landscape, the strength of gravity, the mass of an electron, and crucially, the value of the cosmological constant or dark energy are not fixed. They are like dials that can be set to different values in different pocket universes. Most of these universes would be stillborn or sterile. If dark energy were much stronger, space would have expanded so rapidly after the Big Bang that matter could never have clumped together to form stars, galaxies, or planets. The universe would be a featureless, accelerating void. If dark energy were much weaker or negative, the universe might have collapsed back in on itself in a big crunch long before life could arise. In the unimaginably vast multiverse, every possible value exists somewhere. This is where the anthropic principle enters. It is a simple, almost tautological statement. We can only observe a universe that is compatible with our existence as observers. We find ourselves in a universe with this specific, tiny value of dark energy, not because it is special or predicted by a fundamental equation, but because it is one of the very few values that allows galaxies, stars, and ultimately, curious beings like us to evolve and ask the question. It is a selection effect, like a puddle of water marveling at how perfectly the hole it sits in conforms to its shape. The puddle does not realize there are countless other holes of different shapes. It simply fits the one it is in. This line of reasoning is deeply controversial. To its proponents, it is a necessary and elegant escape from the vacuum catastrophe. It explains why the laws of physics seem so finely tuned for life without requiring a designer. The answer is simply that in a near-infinite ensemble of universes, a few will, by sheer chance, have the right conditions. We are in one of those lucky ones. To its detractors, it is a philosophical surrender, a retreat from the core mission of science to find deterministic, explanatory laws. It replaces a testable prediction with an untestable, almost metaphysical assertion. How could we ever prove or disprove the existence of other universes we can never interact with? The debate cuts to the heart of what science is. Is the anthropic principle a profound insight into the nature of reality, or is it a clever way of saying we will never know? It leaves us staring into the dark, wondering if the mystery of missing energy is not a puzzle to be solved, but a signpost pointing to realities beyond our own. Mund offered a simple fix for galaxy rotations, but the universe demands a theory with far greater ambition. To truly challenge the dark universe, we need a framework that can rewrite gravity not just in the outskirts of galaxies, but across the entire cosmos, from the orbit of Earth to the accelerating expansion of space itself. This is the realm of full-fledged modified gravity theories, a sophisticated class of models that seek to overhaul Einstein's general relativity itself. The most prominent of these is known as F of R gravity. At its heart is a profound alteration to the very foundation of Einstein's equations. In general relativity, the core mathematical object is the Einstein-Hilbert action, which depends linearly on R, the Ricci scalar. This scalar is a single number that encapsulates the curvature of spacetime at a point. Think of R as a cosmic weather report, a measure of how severely space is bent or stretched in a given region. In F of R gravity, this simple linear dependence is replaced by an arbitrary function, F of R. This means gravity's behavior is no longer tied to a simple measure of curvature. Instead, the theory can have a complex, changing relationship with curvature itself. By carefully choosing this function, theorists can engineer new terms in the equations of motion. These extra terms can act like an extra repulsive force on the largest scales, driving cosmic acceleration without any need for dark energy. Simultaneously, on the scale of galaxies, these modifications can alter how gravity behaves in regions of low density or curvature, producing effects that mimic the gravitational pull of dark matter halos. The goal is breathtakingly comprehensive, a single, modified theory of gravity that banishes both dark energy and dark matter from our cosmic ledger, explaining all the anomalies with one elegant stroke. The challenge, however, is one of incredible fine-tuning. Any successful theory must pass stringent local tests. In our solar system, where space-time curvature is mild and we have exquisitely precise measurements from orbiting probes and lunar laser ranging, general relativity has been confirmed with phenomenal accuracy. A viable F of R theory must reduce almost exactly to Einstein's equations in this regime, like a sophisticated new app that runs perfectly on old hardware. It must not predict deviations in the orbit of Mercury or the bending of starlight that we do not see. Yet, on cosmic scales, the same theory must diverge dramatically, producing enough repulsion to explain the universe's accelerated expansion. Crafting a mathematical function that seamlessly bridges these two extremes, that is invisible in our backyard but dominant across the cosmos, is like designing a single material that is soft as silk at room temperature but strong as steel in a vacuum. It is an immense theoretical tightrope walk. Furthermore, many of these models introduce new dynamical fields, often called scalars, which can mediate a fifth force. To remain consistent with observations, this force must be cleverly hidden or screened in dense environments like our solar system, a trick known as chameleon screening. While F of R gravity and its cousins represent a monumental intellectual effort to unify the cosmic anomalies, they often trade the simplicity of adding new components for a daunting complexity in the laws themselves. They ask us whether it is more elegant to populate the universe with invisible substances or to complicate the one force we thought we understood. The quest continues, a high-stakes gamble on the very architecture of reality. The multiverse asks us to accept an infinity of unseen realities, but one far older idea suggested we need not look beyond our own universe at all. The mystery of dark energy rests entirely on one pivotal observation, the redshift of light from distant galaxies. Edwin Hubble interpreted this redshift as a Doppler effect, the stretching of light waves as galaxies race away from us in an expanding cosmos. But what if that interpretation is wrong? In the 1920s, around the same time as Hubble's discovery, a Swiss astronomer named Fritz Zwicky proposed a radically different explanation. He called it the tired light hypothesis. The idea is disarmingly simple. Perhaps light, as it travels across the vast, lonely gulfs of intergalactic space, simply loses energy. Photons might interact ever so slightly with the sparse particles or fields they encounter, or perhaps with the fabric of space itself, causing them to gradually slow down and shift toward the red end of the spectrum. In this view, the redshift is not a measure of velocity or expansion. It is a sign of cosmic fatigue, a record of the immense journey the light has endured. If true, the entire foundation for an expanding universe, and by extension the need for dark energy to drive its acceleration, would crumble. The universe could be static, eternal, and the missing energy would vanish as a misinterpretation. For decades, tired light was a legitimate, if minority, contender. Its appeal lay in its directness. It removed the need for a singular, explosive beginning and the bizarre cosmic ingredients that followed. Yet, as our observational tools sharpened, the hypothesis began to show fatal cracks. Two pieces of evidence in particular delivered the decisive blows. The first comes from distant supernova, the very explosions that revealed cosmic acceleration. When astronomers study these stellar cataclysms, they don't just measure their redshift. They also measure how their light brightens and fades over time, a pattern called the light curve. In an expanding universe, time itself is stretched along with the light. A supernova billions of light-years away should appear to unfold more slowly than a nearby one. Its light curve should be stretched in time, like a song played at a slower speed. This is exactly what we observe. The fading of distant supernova is measurably slower. The tired light hypothesis, however, only affects the photon's energy, not the flow of time. It predicts no such time dilation. A tired photon from a distant supernova would be redshifted, but the explosion would appear to flash and fade at the same rate as a local one. The data clearly shows the stretching, a direct signature of an expanding spacetime that tired light cannot reproduce. The second, even more powerful refutation comes from the cosmic microwave background. This ancient radiation is not just redshifted, it has a nearly perfect blackbody spectrum, the specific thermal fingerprint of an object in complete equilibrium. The expansion of the universe stretches this spectrum, cooling it uniformly from a white-hot glow to a faint microwave whisper, but it preserves its perfect blackbody shape. For tired light to produce this, the energy loss mechanism would have to affect every single wavelength of light with exquisite mathematical precision, exactly as if the radiation had been thermally cooled. No known physical process that saps a photon's energy during travel could achieve this. It would inevitably distort the spectrum, smearing its perfect thermal signature. The fact that we see a pristine blackbody spectrum is one of the strongest confirmations that the redshift is cosmological, a relic of expansion from a hot, dense state. While tired light is now firmly relegated to the history books, its legacy is crucial. It stands as a monument to scientific audacity, a reminder that progress requires us to challenge our most foundational assumptions, even those as seemingly solid as an expanding universe. It was a wrong turn, but one that helped clarify the right path by forcing cosmology to find evidence that could distinguish between a tired photon and an expanding cosmos. The darkness we seek to explain is real, but its nature is written in the stretched time of dying stars and the perfect thermal echo of creation itself. The perfect blackbody spectrum seems to confirm a smooth, uniform expansion, but our telescopes tell a different story. They reveal a universe clumped into a vast cosmic web, a frothy structure of immense galaxy clusters, long filaments and cavernous, nearly empty voids. This glaring contradiction between the large-scale smoothness we assume and the dramatic structure we see forms the core of Theory 12, inhomogeneous cosmology and backreaction. It asks a dangerous question: what if our most fundamental assumption about the cosmos is a convenient fiction? Cosmology rests on the cosmological principle, the idea that on the largest scales, the universe is homogeneous and isotropic, the same everywhere and in every direction. This principle allows us to treat the entire cosmos with simple, smooth equations, like modeling a sponge as a uniform block of rubber, but a sponge is not a solid block. It is mostly empty space with dense knots. Backreaction proposes that this difference is not just a detail, it is the key to the dark energy puzzle. As gravity pulls matter into clusters and filaments, it leaves behind those gigantic voids. These voids are not passive emptiness, they are regions where the gravitational pull is weaker, so space inside them expands faster than the average. Meanwhile, the dense clusters and filaments expand more slowly, held back by their own intense gravity. This creates a cosmic tug-of-war, and the crucial insight is that the average expansion rate of the whole universe is not simply the sum of its parts. The faster expanding voids, because they grow so vast, begin to dominate the volume of the cosmos. Their more rapid stretching pulls the global average expansion rate upward. This effect is called backreaction because the growth of structures reacts back on and changes the very background expansion we use to describe them. From our vantage point, embedded within a galaxy cluster, a relatively overdense region, we are like observers in a slow-moving boat. We look out at other boats in the slow current and at buoys drifting in the fast-moving river beyond. If we mistakenly assume we are all in the same uniform flow, we would conclude that distant buoys are accelerating away from us, pushed by some mysterious force. But there is no phantom force, only the different flow rates of the river. In this view, the observed acceleration of supernova is an illusion of perspective, a consequence of us measuring the cosmos from a slow-moving pocket, while most of the universe's volume is rushing outward in the fast-expanding voids. The computational challenge here is staggering. To prove this, cosmologists cannot use the smooth equations of a homogeneous universe. They must attempt to model the entire cosmic web, billions of light-years across, and calculate how all these interacting regions of fast and slow expansion average out over time. It is like trying to predict the exact changing shape of the world's ocean currents by modeling the motion of every single water molecule. The preliminary results are tantalizing but inconclusive. Some sophisticated simulations suggest backreaction could account for a portion of the observed acceleration, perhaps even all of it, while others find the effect is too small, merely a ripple on the tide of a true dark energy. The theory forces a profound philosophical shift. It suggests we may be cosmic cartographers trying to map a rugged, fractal coastline using only the smooth curves of a globe. The darkness we measure may not be an unknown energy, but the shadow of our own oversimplified map, a reminder that the universe's true geometry is written in the wild, uneven distribution of its emptiness. The uneven tug-of-war between voids and clusters reshapes our cosmic map, but one of the most provocative new theories points to a far more dramatic source for the missing energy, lurking in the universe's most terrifying objects. Black holes, those infamous cosmic engines of destruction, might hold a secret role as the architects of cosmic acceleration. This idea, known as cosmological coupling, flips our understanding of black holes on its head. We have always thought of them as endpoints, final graves for matter and light. But what if they are also seeds of creation, their hidden cores intimately tied to the expansion of the universe itself? The theory hinges on a radical reimagining of a black hole's interior. According to general relativity, at the very center lies a singularity, a point of infinite density where our laws of physics break down. Cosmological coupling proposes that within this unfathomable point, the vacuum energy of space, the same energy that causes the vacuum catastrophe, is trapped and locked away. This energy is not static. As the universe expands, the vacuum energy density inside the black hole is cosmologically coupled to that expansion, causing the black hole's mass to grow. It is not feeding on stars or gas. It is gaining mass simply because the space it contains is coupled to the expanding cosmos outside. Think of a black hole not as a static pit, but as a balloon being gently inflated by the expansion of the universe itself. The air inside the balloon is the vacuum energy, and as the universe grows, so does the balloon, and with it, the amount of trapped air. Now consider the sheer number of black holes in the universe. Every massive galaxy has a supermassive black hole at its heart, and there are countless stellar mass black holes scattered among the stars. If all of them are cosmologically coupled, their combined growing mass could account for the precise amount of dark energy we measured driving the universe apart. The vacuum energy is not smoothly spread throughout space. It is bottled up inside these cosmic containers, and their collective growth provides the repulsive push. This is a breathtakingly elegant, if unsettling, idea. It unifies the universe's most destructive phenomenon with its most mysterious driving force. The search for evidence has turned to some of the oldest, quietest black holes in the cosmos. Astronomers are studying elliptical galaxies, which are thought to be cosmic retirement homes where star formation has long since ceased. The supermassive black holes at their centers are dormant, having consumed the nearby gas and dust eons ago. According to standard models, these black holes should not have grown significantly for billions of years. But if cosmological coupling is real, they should have steadily gained mass simply by existing in an expanding universe. By comparing the masses of black holes in ancient elliptical galaxies to those in younger galaxies, scientists hope to see a telltale sign of this passive growth over cosmic time. Early analyzers have suggested that black holes in these old galaxies appear to be several times more massive than expected, a possible hint that coupling is at work. The findings are hotly debated and much more data is needed. If confirmed, it would mean that dark energy is not a feature of empty space, but a collective property of the universe's darkest inhabitants. The monsters in the galactic basement would not just be lurking, they would be, in their own silent way, building the future of everything. Black holes may bottle up the vacuum energy, but what if the problem is not with the contents of the universe, but with the very rules that govern it? The laws of physics feel eternal and fixed. The speed of light is a universal speed limit. The strength of gravity is a constant pull. These fundamental constants are the bedrock of our reality. Yet a radical and persistent idea suggests this bedrock might be shifting sand. What if these constants are not constant at all? What if they have been slowly changing over the 14 billion-year lifetime of the cosmos? This is Theory 14, the possibility of time varying fundamental constants, and it offers a breathtakingly different path to dark energy. If a constant like Newton's gravitational constant, big G, were to weaken over time, the force of gravity across the entire universe would be subtly diminishing. In the equations of cosmology, a weakening gravity would look exactly like a new repulsive force pushing things apart. The cosmic acceleration we measure would not be driven by a mysterious dark energy, but by the slow fading of the universe's most familiar force. Similarly, if the speed of light were different in the past, it would alter how we interpret the redshift of distant galaxies, potentially rewriting the entire expansion history. The mathematical framework for this is often found in scalar tensor theories, extensions of Einstein's general relativity. In these theories, alongside the familiar tensor field of gravity, there exists a scalar field, a kind of cosmic background value that can change from place to place and from time to time. This scalar field directly couples to gravity, effectively making the strength of gravity a dynamic property set by the value of this field. As the universe expands and cools, this field evolves, and so does the gravitational constant. The expansion of space itself can drive this change, creating a feedback loop where expansion alters gravity, which in turn alters the expansion. The idea is not new. In the 1930s, physicist Paul Dirac noticed a strange numerical coincidence, his large numbers hypothesis. He saw that ratios of certain cosmic numbers, like the age of the universe to the time it takes light to cross an atom, were enormous and roughly comparable. He speculated this was not a coincidence, but a sign that fundamental constants must change in relation to one another over time to keep these ratios in balance. While Dirac's specific model has not held up, the seed of the idea was planted. Today, the search for varying constants is a precise and urgent science. Astronomers use the light from incredibly distant quasars as cosmic time capsules. As this light travels for billions of years, it passes through ancient clouds of gas, imprinting a fingerprint of the atomic physics of that era. By analyzing the fine structure of these absorption lines, scientists can check if the fine structure constant, which governs the strength of electromagnetism, was different in the distant past. Some controversial studies have claimed to detect a tiny variation, though the results are fiercely debated. On Earth, we have our own natural laboratory, the Oklo uranium deposit in Gabon. 2 billion years ago, this site naturally formed a series of self-sustaining nuclear fission reactors. The nuclear reactions that occurred there were exquisitely sensitive to the values of fundamental constants. By analyzing the precise mix of nuclear waste products left behind, physicists can probe whether the constants were different 2 billion years ago. So far, the Oklo evidence suggests remarkable stability. The hunt continues because the implications are staggering. If a varying constant is the true cause of cosmic acceleration, then dark energy is an illusion, a misinterpretation of a cosmos where the rulebook itself is being slowly rewritten. We would not need to find a new ingredient. We would need to accept that the oldest ingredients we know are not what they seem. The mystery of the missing energy might be the universe's way of telling us its most basic rules are still being written. If the laws of physics themselves can change, then perhaps the entire history of our cosmos can repeat. The most enduring myth of time is the cycle, and modern cosmology has dared to give it a mathematical form. This is the realm of cyclic universe models, theories that banish the idea of a single, definitive beginning and replace it with an eternal, repeating loop of creation and destruction. In these visions, dark energy is not an anomaly leading to an empty end, but an essential engine powering the cosmic cycle itself. The most sophisticated of these ideas emerges from the depths of string theory and is known as the ekpyrotic universe. The name comes from the Greek word for conflagration, and its origin story is nothing short of spectacular. It proposes that our three-dimensional universe is not all there is. Instead, it is a three-dimensional membrane or brain floating in a higher dimensional space, parallel to us, just a microscopic distance away in this hidden dimension, floats another three-dimensional brain, a separate, complete universe. These two brains are drawn together by a force oscillating in an endless, slow dance. Every trillion years or so they collide. That collision is not a catastrophe. It is our Big Bang. The immense kinetic energy of the impact is converted into the seething hot plasma of matter and radiation that filled our nascent cosmos. The universe expands and cools from this event, exactly as we observe. But here is where dark energy enters the plot with a starring role. After the collision, the brains bounce apart and begin to drift slowly away from each other. As they separate, a mysterious attractive force between them, modeled by a field, begins to act. This force gradually pulls them back together for the next collision. In the equations, this attractive force manifests in our brain as a form of dark energy with a very specific property. It is a constant, gentle negative pressure that causes the expansion of our universe to accelerate. This is not a coincidence. The acceleration is crucial. It serves to smooth out and flatten the universe completely, wiping away any irregularities, any cosmic scars from the previous cycle. It prepares a clean, uniform slate. As the brains approach their next collision, this dark energy field transforms, its potential energy dropping, driving the universe toward a period of contraction, a big crunch. But this is not a chaotic collapse into a singularity. Because the dark energy has made everything so perfectly smooth and flat, the contraction is similarly uniform and controlled. The universe contracts evenly, heats up, and then, at the moment the brains collide again, rebounds in a new Big Bang, starting the cycle anew. Dark energy in this model is the cosmic reset button. Its presence and its specific value are not random. They are the necessary conditions for the cycle to continue eternally. It exists to cleanse the universe, to ensure each new cycle begins with the same pristine conditions, allowing galaxies, stars, and life to form again and again. This stands in stark contrast to other, simpler cyclic models, like the classic Big Bang followed by Big Crunch idea. In those older visions, a universe dominated by matter would eventually collapse under its own gravity in a fiery, chaotic implosion, only to rebound. But such a chaotic crunch would likely scramble information and structure beyond recognition, making a true cyclic renewal impossible. The ekpyrotic model, with its elegant brane collisions and dark energy-driven smoothing, provides a mechanism for a true, orderly rebirth. It transforms dark energy from a herald of a cold, lonely end into the guarantor of cosmic immortality, the quiet force that ensures the story of the universe never truly ends but only turns the page. A cosmic cycle promises renewal, but it requires a universe that can clean its own slate. What if the dark sector itself is responsible for this cosmic housekeeping? The shadows we call dark matter and dark energy might not be strangers but family, with one transforming into the other. This is the provocative idea behind dark matter decay or annihilation. Instead of two independent mysteries, we could be witnessing a single substance changing phase over cosmic time, like ice melting into water. The most straightforward version of this theory proposes that dark matter particles are not perfectly stable. Over the eons, they could undergo a slow, radioactive-like decay into lighter particles. This decay would release energy. In the early, dense universe, dark matter's gravitational pull dominated, sculpting galaxies. But as it decays, its density gradually decreases, while the energy released from the decay begins to infuse the vacuum of space. This infusion could manifest as a constant, repulsive pressure, taking over as the dominant force and driving the acceleration we see today. The baton of cosmic influence is passed within the dark sector itself. Another, more dynamic variation involves annihilation. We know from particle physics that when matter meets antimatter, they annihilate in a flash of energy. Some models suggest that dark matter particles could be their own antiparticles. In the early universe, when dark matter was densely packed, these particles would have frequently collided and annihilated, but the process would have been balanced by new particles being created from the hot plasma. As the universe expanded and cooled, this equilibrium broke and most annihilation stopped. However, a residual, slow-burning annihilation could have persisted. If the products of this late-time annihilation include extremely light, weakly interacting particles, they could essentially become a form of dark radiation or a field that exerts negative pressure. The energy output from this lingering process could subtly shift the expansion history of the universe, mimicking the effect of dark energy. The elegance is profound. One unknown, dark matter, naturally evolves to produce the second unknown, dark energy, linking the two greatest puzzles with a single narrative thread. The challenge, however, is one of exquisite timing. Any such process must be carefully calibrated to match the cosmic calendar we observe. Dark matter had to be stable enough and dominant enough for billions of years to allow galaxies and clusters to form. Its decay or annihilation could not have started too early, or it would have washed away the delicate seeds of structure. Yet it had to become significant at just the right moment, roughly 5 billion years ago, to kickstart the acceleration we measure. Getting the physics to align this timeline is like tuning a clock with hands that are 14 billion years long. Furthermore, such models often predict specific signatures in the cosmic microwave background or in the distribution of galaxies today, subtle wrinkles that might distinguish them from a simple cosmological constant. So far, the smooth, featureless acceleration we see fits the simplest model best, putting pressure on these more complex transformation stories. They remain a compelling frontier, a reminder that the darkness may not be static, but a dynamic player in its own epic story of change. A dynamic dark sector transforms over time, but could the key to acceleration be locked in the very shape of space? The quantum world holds a strange and proven phenomenon that might scale up to cosmic proportions. In a laboratory, if you take two perfectly smooth, uncharged metal plates and bring them incredibly close together in a vacuum, something bizarre happens. They are pulled toward each other by an invisible force. This is the Casimir effect, and it is not magic. It is a direct consequence of the quantum vacuum. Remember that seething sea of virtual particles popping in and out of existence everywhere. These quantum fluctuations can be thought of as waves of all possible wavelengths filling empty space. When you insert two plates very close together, you impose a boundary condition. Only certain wavelengths of these virtual waves can fit between the plates. Outside the plates, all wavelengths are still possible. This creates a pressure imbalance. There are more possible quantum fluctuations pushing on the outside of the plates than on the inside. The result is a net inward force pulling the plates together. It is a measurable force generated by nothing but the structured emptiness of space itself. Now take this laboratory curiosity and inflate it to the size of the cosmos. Could the entire universe, by virtue of its own shape, age, or hidden dimensions, create a similar imbalance in the quantum vacuum? Could this imbalance manifest not as an attraction, but as a repulsion, pushing everything apart? This is the speculative leap of Theory 17, the search for a cosmological Casimir effect. The idea is that the universe itself might have boundary conditions or a topological structure that filters the quantum vacuum in a specific way. One possibility involves the universe's finite age. We can only observe a spherical region of space called the particle horizon. The distance light has had time to travel since the Big Bang. This horizon acts as a kind of boundary for causal influence. Some theorists propose that this causal boundary could play a role analogous to the Casimir plates, restricting the modes of quantum fluctuations that can contribute to the vacuum energy within our observable universe. The calculation is fiendishly complex, but the tantalizing result is that such a boundary could yield a small, constant vacuum energy density, a cosmological constant emerging naturally from quantum physics and the simple fact that the universe has a finite past. Another, even more exotic avenue explores the universe's possible compact dimensions. String theory suggests there may be more than the three spatial dimensions we experience. The extra dimensions could be curled up on themselves, fantastically small and hidden. If these compact dimensions have a specific size and shape, they too would impose boundary conditions on quantum fields. The vacuum energy would depend on the geometry of this full, higher dimensional space. By carefully choosing the topology, physicists might be able to derive a small, positive dark energy from these hidden geometries. The cosmic Casimir energy would not be an added ingredient, but a signature of the universe's hidden architecture. While these ideas are highly theoretical and far from proven, they represent a profound shift in thinking. They suggest dark energy may not be some foreign substance or field we must discover. It could be an inevitable energy of confinement, a whisper of the quantum vacuum heard only because the cosmos itself has walls or a shape or a finite history. The force accelerating the galaxies could be the gentle pressure of the universe's own geometry on the endless hum of nothingness. The quantum vacuum's hum suggests space is not empty, but what if it is not even space as we know it? Superfluid vacuum theory proposes something far more radical. It suggests that spacetime itself is not a static stage. Instead, it is a dynamic, flowing medium, a kind of cosmic superfluid. Think of the universe not as a void dotted with objects, but as an unimaginably vast, frictionless ocean. In this model, the fundamental building blocks of reality, the particles we call electrons and quarks, are not tiny dots. They are excitations in this superfluid, like ripples, whirlpools, or sound waves moving through the cosmic sea. This is a breathtakingly ambitious framework, one that seeks to derive the laws of particle physics from the properties of this underlying fluid. Now, where does dark matter fit into this flowing cosmos? Within any superfluid, you can have defects, stable imperfections in its structure. A common example is a vortex, a microscopic whirlpool that gets trapped in the flow. In the superfluid vacuum of spacetime, such defects could be incredibly massive and stable, forming intricate networks or clumps. These would not be particles in the traditional sense. They would be knots in the fabric of reality itself. Crucially, these topological defects would interact with ordinary matter almost exclusively through gravity, as their nature is tied to the spacetime medium, not the electromagnetic force. They would be invisible, yet their gravitational pull would be immense. In this view, the dark matter halos enveloping galaxies are not swarms of unknown particles. They are vast, slow-moving storms of spacetime vortices, permanent wrinkles in the superfluid medium that tug on stars with their hidden mass. This elegantly explains why dark matter seems to only whisper through gravity. It is not passing through space, it is an architectural feature of space. And what of dark energy? Here, the superfluid vacuum offers another profound connection. Every quantum system has a ground state, its lowest possible energy level. For this cosmic superfluid, that ground state energy would permeate all of existence. This baseline hum of the flowing spacetime medium could manifest precisely as a cosmological constant, a uniform, repulsive energy inherent to the vacuum itself. The dark energy accelerating the universe would simply be the natural energy flow of the superfluid from which everything is made. The ambition here is staggering. Superfluid vacuum theory does not just add new pieces to the puzzle. It attempts to replace the entire puzzle box. It seeks to unify the description of particles, dark matter, and dark energy under a single, fluid dynamical principle, suggesting that the universe's greatest mysteries are not separate entities, but different behaviors of one coherent, flowing substance. The cosmos, in this vision, is a single, self-interacting ocean, and we are but complex waves upon its surface, trying to understand the nature of the depths that both carry us and shape our destiny. The superfluid cosmos is a sea of possibility, but we already know of ghostly particles that flow through everything. Neutrinos are the universe's most abundant particles with mass, trillions of which pass through your body every second, leaving no trace. They are almost nothing, yet their collective weight could tip the cosmic scales. Their journey from the Big Bang to today offers a subtle clue to the dark energy puzzle. Neutrinos were born in the furnace of the early universe, moving at nearly the speed of light. In this relativistic state, their energy behaved like radiation, a form of energy that pushes against gravity's pull and helps smooth out the cosmos. But as the universe expanded and cooled, these neutrinos slowed down. Their immense kinetic energy faded, and they transitioned to behaving like cold, slow-moving matter. This shift from a relativistic component to a non-relativistic one is a crucial detail in the universe's expansion history. Cosmologists must account for this transition in their models of the cosmic microwave background and large-scale structure. While ordinary neutrinos are too light to constitute dark matter themselves, their changing influence acts as a delicate dial, fine-tuning the precise moment when matter's dominance began to wane. If neutrinos had different masses, the timeline of cosmic evolution would shift. This hints that the properties of even the faintest particles are woven into the story of acceleration. But what if there is a heavier, even more elusive cousin to these ghosts? This brings us to sterile neutrinos, one of the most compelling candidates for warm dark matter. Unlike ordinary neutrinos, which interact via the weak nuclear force, sterile neutrinos, as the name implies, do not. They would feel only gravity, making them utterly dark and nearly impossible to detect directly. Their proposed mass is not a tiny fraction of an electron volt, but in the range of kilo-electron volts, heavy enough to clump under gravity, but light enough to explain why dark matter halos appear less cuspy and dense in the centers of some galaxies than cold dark matter models predict. They are a bridge between the known world of particles and the unknown nature of dark matter, yet their potential role does not end there. In some theoretical models, sterile neutrinos are not inert. They could oscillate with ordinary neutrinos, a quantum dance between the visible and dark sectors. This interaction could be governed by a new field, and as the universe expands, the energy density of this coupled system could evolve in a way that produces an effective negative pressure at late times. Essentially, the behavior of this sterile neutrino field, as it settles into its lowest energy state across the cosmos, could mimic the effects of a cosmological constant or a dynamical dark energy. It is a breathtaking synthesis, suggesting that the solution to both dark matter and dark energy might not be two separate entities, but different aspects of a single hidden particle family. The sterile neutrino remains hypothetical, its existence inferred only from tantalizing anomalies in certain nuclear decay experiments and astrophysical observations. But it represents a powerful idea that the shadows we chase may be made of particles that are not entirely alien, but relatives of the faintest sparks we already know, their hidden lives dictating the fate of all we see. Gravity's emergence from information leads us to a deeper, more universal principle, one that governs everything from steam engines to the fate of galaxies. This is the realm of entropy, the measure of disorder in a system, and its connection to gravity may rewrite the origin of dark energy itself. Building on the idea of emergent gravity, theorists like Eric Verland and Thanu Padmanabhan propose that gravity is not a fundamental force but an entropic force. This is a profound shift. An entropic force is not a push or a pull in the traditional sense. It is the statistical tendency of a system to move toward a state of higher entropy, of greater disorder. A classic everyday example is a stretched rubber band. When you let it go, it snaps back. The force that pulls it is not a fundamental interaction between atoms. It is the result of the polymer molecules inside the band having a vastly larger number of possible tangled, disordered states compared to the ordered, stretched state. The band contracts because the universe favors that higher entropy, tangled configuration. Entropic gravity applies this logic to the cosmos. The theory suggests that what we perceive as the gravitational attraction between two masses is actually the result of the universe's drive to maximize entropy associated with the information stored on a cosmic horizon. Imagine the empty space between two objects. According to holographic principles, the information describing that space is encoded on a distant boundary. When you bring two objects together, you change the arrangement of that information. The system finds that the entropy, the number of microstates describing the information, is higher when the objects are closer together. So they move together not because of a mysterious pull, but because the cosmos is statistically driven toward that higher entropy configuration. It is gravity as a cosmic tendency toward disorder. Now apply this breathtaking logic to the entire universe. The accelerating expansion driven by dark energy could be the ultimate expression of this entropic drive. As the universe expands, new space is created. With that new space comes new horizons and new capacity for information. The universe's total entropy is not constant, it is increasing as the cosmic volume grows. In this view, the acceleration is not powered by a phantom field or a cosmological constant. It is powered by the universe's relentless thermodynamic urge to maximize its entropy. The repulsive push of dark energy is simply the universe favoring configurations where it can become more disordered on the largest possible scale. Padmanabhan's work provides a striking mathematical formulation for this. He showed that the equations governing cosmic acceleration can be derived directly from the difference in the thermodynamic degrees of freedom between the surface of the cosmos and its volume. Essentially, the dynamics of the entire universe, including its acceleration, emerge from the natural tendency to balance the information content at its boundary with the energy within. This provides a thermodynamic origin for dark energy, grounding it not in a new substance, but in the oldest and most universal law we know, the second law of thermodynamics. The universe expands because it must, because the arrow of time and the increase of entropy demand it. The darkness pushing everything apart might not be an energy at all, but the signature of the cosmos endlessly seeking its own most probable, most disordered state. Entropy drives the universe toward its most probable state, but what if our entire cosmos is just one possibility in a near-infinite array of realities? This brings us to the string theory landscape, a breathtaking mathematical vista that does not just allow for dark energy, but demands its bewildering variety. String theory, our most promising framework for a theory of everything, suggests the fundamental ingredients of reality are not point-like particles, but tiny, vibrating loops of energy. The way these strings vibrate determines the properties of every particle and force we see, but the mathematics of string theory are not unique. They do not yield one perfect universe. Instead, they describe a colossal landscape of possible universes, each corresponding to a different stable or metastable vacuum state. Imagine a vast cosmic mountain range with countless valleys. Each valley represents a possible vacuum, a state of empty space with its own specific laws of physics and its own value for the cosmological constant, the vacuum energy. Some valleys are deep and stable, representing universes that could last for eternity. Others are shallow, metastable dips, representing universes that might eventually decay into a lower energy state. In this landscape, the fundamental constants are not fixed by a single equation. They are environmental, like the temperature or air pressure in a particular valley. Our universe, with its specific particle masses and forces, simply occupies one particular valley among perhaps 10 to the 500 others. This is where dark energy finds its home, or rather, its near-impossible needle in a cosmic haystack. The vacuum energy in each valley can be positive, negative, or zero. A positive value acts like dark energy, causing accelerated expansion. A negative value would cause the universe to collapse. Most values generated in the landscape are enormous, on the scale of the catastrophic vacuum energy predicted by quantum field theory. Finding a valley with a value as infinitesimally small as the one we observe, roughly 120 orders of magnitude below the naive prediction, is like searching for a single, specific grain of sand on every beach on every planet in the observable universe. The fact that we exist in such a bizarrely tuned valley is the central puzzle. This leads directly to the multiverse and anthropic reasoning. If the landscape is real and the number of vacua is effectively infinite, then every possible value, no matter how unlikely, will be realized somewhere. We find ourselves in a universe with a tiny, positive cosmological constant, not because it is common, but because it is a prerequisite for the formation of galaxies, stars, and life. The landscape provides the playground, and the anthropic principle explains why we are in this particular corner of it. Yet for this picture to hold, string theorists face a monumental challenge. They must prove that our kind of universe, with its small, positive dark energy, actually exists as a possible valley in the landscape. This is the problem of constructing a de Sitter vacuum, a stable universe with a positive cosmological constant. For years, it was unclear if string theory allowed for such a thing at all. Then came a potential breakthrough known as the KKLT mechanism, named after its creators. The challenge involves stabilizing moduli fields. In string theory, our familiar three-dimensional space is complemented by extra, curled-up dimensions. The size and shape of these extra dimensions are described by moduli fields. If these fields are not fixed, they would behave like massless particles, causing the constants of nature to change in ways we do not observe. The KKLT mechanism uses a clever combination of ingredients from string theory, like fluxes, which are generalized magnetic fields threading the extra dimensions, and non-perturbative effects from objects called D-branes. These ingredients work together to lift the landscape, sculpting a small, shallow valley with a positive vacuum energy. It is like using a combination of carefully placed supports and tensions to create a tiny, stable dimple on an otherwise steep mountainside. The existence of such a de Sitter vacuum remains one of the most heated debates in theoretical physics. Some argue the constructions are not fully stable or that they rely on assumptions that may not hold. Others see it as a promising path forward. The landscape framework, whether it ultimately proves correct, has irrevocably changed the conversation. It suggests that the value of dark energy may not be derivable from a beautiful, unique equation. Instead, it might be a historical accident, a random coordinate in an unimaginably vast cosmic atlas, leaving us to wonder if the ultimate explanation for the universe's missing energy is simply that we are here to notice it. The landscape of string theory is not just a collection of abstract valleys. It is a higher dimensional reality where our entire cosmos might be a thin slice, a membrane adrift in a deeper sea. This is brain cosmology, and it reimagines the universe as a three-dimensional brain, short for membrane, existing within a vast, unseen higher dimensional space called the bulk. Imagine our three-dimensional world not as all there is, but as the surface of a vast, impossibly thin sheet of paper floating in a four-dimensional ocean. We are confined to that sheet, unable to perceive the ocean's depth, but its presence shapes everything. In this picture, the particles and forces we know, like electrons and light, are like ink or vibrations trapped on the paper's surface. They cannot leave the brain. Gravity, however, is different. It is the ripple in the very fabric of space-time, and in these models, gravity can leak off our brain and propagate into the bulk. This leakage is a revolutionary idea. If gravity's lines of force can spread out into an extra dimension, then its strength would diminish faster with distance than Isaac Newton or Albert Einstein predicted in a purely three-dimensional world. On the scale of our solar system, this effect would be negligible, but across the vast distances of a galaxy, the weakening could be significant. The consequence is startling. The reason galaxies seem to need extra, unseen mass to hold together might not be because dark matter is there, but because gravity is subtly weaker on these large scales than we assumed. The observed rotation of galaxies could be explained not by invisible halos, but by the quiet seepage of gravity into hidden dimensions. For dark energy, the brain itself holds the key. A membrane under tension, like the skin of a drum, has an inherent energy. The tension of our three-dimensional brain, stretched across the cosmos, could manifest as a constant energy density permeating all of space. This is not a substance added to the universe. It is a property of the universe's very structure, its foundational fabric. This brain tension could be the cosmological constant, the engine of cosmic acceleration. Furthermore, the brain's interaction with the bulk can generate this effect. If the bulk contains its own energy fields, or if our brain is slowly moving or evolving within the bulk, that dynamic relationship could produce an effective repulsive force on our brain, driving galaxies apart. The bulk becomes the ultimate source of the push, a hidden ocean whose currents gently inflate our floating membrane. To make this tangible, think of a water strider insect skating on a pond. The pond's surface is the brain, our universe. The strider and any dust particles are like stars and galaxies confined to the surface. The water below is the bulk. Ripples on the surface, like light or matter, stay on the plane, but some influences, like very subtle pressures or currents from the water below, can affect the tension and expansion of the surface itself. Brain cosmology asks us to accept that the deepest mysteries of the cosmos might be solved not by what is in our universe, but by the shape and tension of the slice we call home. This bizarre timing is the universe's quietest, most persistent whisper of a problem. Why now? Of all the trillions of years in our cosmos's potential lifespan, we find ourselves in the brief sliver where the density of dark energy and the density of matter are roughly comparable. For billions of years, matter's gravitational pull dominated, slowing the expansion. Now, dark energy's repulsive push has taken over, accelerating it. The transition happened only about 5 billion years ago, a cosmic blink. If the cosmological constant is truly constant, an immutable property of the vacuum, then its energy density has been exactly the same since the first instant of the Big Bang. Meanwhile, the density of matter has been plummeting as the universe expands and dilutes. This means their ratio has been changing dramatically over time. For them to be of the same order of magnitude right now in our cosmic epoch is a staggering coincidence. It is as if you walked into a vast, empty auditorium just as a single, falling leaf crossed the path of a single, drifting dust mote. The odds seem impossibly fine-tuned. This coincidence problem is arguably more troubling than the vacuum catastrophe's giant numbers because it questions not the value of dark energy but the timing of its dominance. A true constant offers no explanation for why we live at this special moment. It simply is, leaving us to marvel at our inexplicably lucky placement in cosmic history. This is where rival theories launch their most compelling attacks. Dynamic models like quintessence see the coincidence not as luck but as natural history. In these models, the dark energy field evolves. Perhaps it was dormant or weak in the early universe, allowing matter to clump and form galaxies without interference. Only as the universe expanded and cooled did the field roll to a new configuration, its repulsive power growing to overtake matter's grip. The timing is not a coincidence, it is a phase in the field's life cycle, a chapter we are observing simply because complex life requires the long, stable epochs that came before. The anthropic principle from the multiverse perspective addresses the coincidence head-on by embracing it as a selection effect. In the infinite landscape of universes, dark energy takes every possible value. In the overwhelming majority, it is either far too strong, preventing any structure from ever forming, or far too weak, causing a premature collapse. Universes where the values are comparable for long periods are exceedingly rare, but observers can only arise in those rare universes where structure had time to form, and where the acceleration had not yet ripped everything apart. We find ourselves at this moment not because it is likely, but because it is necessary for our existence. The timing is written into the prerequisites for life itself. Each approach reflects a different philosophical stance. Quintessence seeks a dynamical, physical mechanism within our universe's story. The anthropic principle looks outward to an ensemble of realities and invokes probability and observation. The true test for any theory of dark energy, beyond fitting the observational data, is whether it can naturally explain why the cosmos looks this way to us right now. The quiet question of timing may be the loudest clue we have. The coincidence of timing whispers of a deeper connection, a hint that the two great shadows might be linked. But to understand that potential union, we must first look closely at the individual suspects. While dark energy commands the narrative of acceleration, dark matter forms the hidden skeleton of the cosmos, and its true identity remains a maddening blank. The hunt has narrowed to a few prime suspects, each with a compelling backstory and a frustrating lack of evidence. First, the aristocratic favorite for decades, weakly interacting massive particles, or WIMP. Their appeal lies in a beautiful concept known as the WIMP miracle. In the early universe, a zoo of exotic particles should have been created in the hot Big Bang. Most of these would have quickly annihilated with their antiparticles, disappearing in flashes of energy. But if there existed a stable, massive particle that interacted only through the weak nuclear force and gravity, its annihilation rate would have naturally frozen out as the universe expanded and cooled. leaving behind just the right relic density to account for all the dark matter we observe today. It is a prediction that emerges elegantly from supersymmetry, a leading extension of the standard model of particle physics. WIMP would be heavy, perhaps 100 to 1,000 times the mass of a proton, and they would flood the galaxy, streaming through Earth by the trillions every second. To catch one, scientists have built exquisite traps deep underground, in abandoned mines and beneath mountains, shielded from cosmic rays. These detectors use ultra-pure crystals or vats of liquid xenon, waiting for the impossibly rare moment a WIMP might bump into an atomic nucleus and release a whisper of light or charge. After decades of searching with ever more sensitive instruments, the silence is growing deafening. Not a single confirmed WIMP signal has been found. Then we have the gentle ghost, the action. Born from a completely different puzzle, the action was proposed to solve a profound mystery in quantum chromodynamics, the theory of the strong nuclear force. The equations allowed for a violation of a symmetry called CP, which would make the neutron possess a large electric dipole moment, a kind of lopsided charge distribution. We have measured the neutron, and it is perfectly round to an incredible precision. To explain this, physicists proposed a new, very light particle that would quietly suppress this violation. The action would be billions of times lighter than an electron, a wisp of a thing. But in the dense early universe, they could have been produced in such staggering numbers that their collective mass adds up to all the dark matter. Unlike WIMP, actions would behave less like discrete particles and more like a pervasive, coherent field oscillating throughout space. To find them, scientists are building enormous, powerful magnets. Inside these magnets, actions should very rarely convert into microwave photons. It is like tuning a cosmic radio across a band of frequencies, listening for a specific, faint tone that has never been heard. The search is meticulous and ongoing, a hunt for a whisper in a magnetic storm. Finally, there is the mundane, yet equally elusive candidate, massive compact halo objects or MACHO. These are not exotic particles at all. They are ordinary, baryonic matter in its darkest forms, objects like black holes, neutron stars, very faint old stars, or rogue planets that simply do not glow. They would reside in the halos of galaxies, invisible but massive. The primary method to find them uses a phenomenon called gravitational microlensing. If a MACHO passes directly between us and a distant star, its gravity will act as a lens, briefly magnifying the star's light. Astronomers have monitored millions of stars for these telltale brightenings. The results were definitive but disappointing. While some MACHO were found, their total mass accounts for only a tiny fraction of the dark matter halo. The vast majority of the darkness cannot be made of these failed stars or stellar remnants, so the search continues, a three-pronged investigation into the impossible. A heavy particle that refuses to show itself, a ghostly field that will not sing its note, and ordinary dark objects that are nowhere near abundant enough. Each dead end is a clue pushing us toward a more radical realization. Perhaps the answer does not lie in finding one of these suspects, but in realizing that the missing mass and the missing energy are two symptoms of a single, deeper disturbance in the laws of nature. The ultimate fate of the cosmos hinges entirely on the true nature of the shadow we call dark energy. Each theory paints a vastly different portrait of the deep future, a gallery of endings ranging from silent dissolution to cosmic rebirth. If the cosmological constant is correct, our universe is on a gentle, inexorable cruise into emptiness. Billions of years from now, after the last stars have burned out and galaxies have merged into giant elliptical graveyards, the constant repulsion will continue its work. The space between gravitationally bound galaxy clusters will stretch faster and faster. From the perspective of any remaining ember of a civilization huddled around the fading heat of a black hole, the observable universe will shrink. Distant galaxy clusters will redshift beyond detection, their light stretched to wavelengths longer than the universe itself. One by one, they will vanish from the sky, not by moving, but by the expansion of space, making the distance between them and us increase faster than light can cross it. Eventually, each isolated structure will be surrounded by an absolute, eternal horizon of darkness, a future of profound and lonely stillness where time itself may lose all meaning. This bleak fade stands in stark contrast to the apocalyptic finale promised by phantom energy. Here, the acceleration is not gentle but exponential, a runaway feedback loop of repulsive gravity. In this future, the universe does not quietly drift apart, it is violently shredded. First, galaxy clusters are torn asunder, their member galaxies flung into the void. Then the phantom force intensifies, overcoming the gravity that binds individual galaxies. The Milky Way and Andromeda, destined to merge in a few billion years, would instead be ripped apart before they ever meet. The horror moves inward. As the repulsion surpasses the strength of solar systems, planets are torn from their stars. In the final, finite moments before the Big Rip, the phantom force exceeds the nuclear forces holding atoms together. Planets, rocks, and finally every molecule and atomic nucleus in the cosmos would be disassembled in a flash. Space-time itself would be torn asunder, a definitive and violent end to causality and structure. Yet other futures offer a twist, a potential for return. In some quintessence models, the dark energy field could decay or reverse its course. Imagine the acceleration we see today not as a one-way ticket to emptiness, but as a cosmic inhale before a great exhale. The repulsive push could gradually weaken, allowing gravity to reassert its dominance. The expansion would slow, halt, and then reverse. Distant galaxies, their light now shifted to the blue, would begin to approach. The universe would contract, heating up as it does. The cosmic microwave background, that faint whisper of the Big Bang, would grow hotter and brighter, first to a glow, then a searing heat. Galaxies would merge in a fiery chaos, stars would be torn apart, and all structure would be compressed back toward an unimaginably dense, hot state. This big crunch could be a true end, or it could be a bounce, a gateway to a new cycle. This cyclical vision finds its most elegant form in the ekpyrotic model. Here, dark energy is the cosmic reset button, smoothing the universe perfectly flat to prepare for the next collision of brains. In this future, our universe continues to accelerate, becoming ever more uniform and empty. But this emptiness is not an end. It is the necessary prelude to renewal. When conditions are just right, the hidden dynamics of the higher dimensional bulk draw our brain toward its neighbor once more. They collide in a new fiery bang, and a fresh universe is born from the ashes of the old, with its own stars, galaxies, and perhaps its own curious beings to ponder the darkness. The cycle repeats potentially forever, an eternal return written into the geometry of reality itself. The choice between these futures, a lonely fade, a violent rip, a crushing reversal, or an endless cycle, rests on the identity of a force we cannot see, a decision made in the dark that will echo for eternity. The final fate of the cosmos is written in data, not just in theory. Our journey through 30 possibilities rests on 4 unshakable pillars of observation, each a different way of listening to the universe's story. The first pillar came from the light of dying stars. Distant Type 1 a supernova act as cosmic lighthouses, their known brightness allowing us to measure their distance with incredible precision. When astronomers in the late 1990s compared that distance to the supernova's redshift, they made the shocking discovery that the most distant ones were fainter than expected. The universe was not just expanding, its expansion was accelerating, a finding that earned a Nobel Prize and forced dark energy into the spotlight. The second pillar is the oldest light of all, the cosmic microwave background. The Planck satellite mapped its subtle temperature variations with exquisite detail. These tiny wrinkles are a frozen record of the universe's infant geometry and composition. By analyzing their patterns, cosmologists could measure the total density of the universe and the proportion of ordinary matter, dark matter, and dark energy with a precision of about 1%. The data tells us dark energy makes up roughly 68% of the cosmic pie. The third pillar uses the universe itself as a ruler. In the early cosmos, sound waves propagated through the hot plasma, creating a characteristic scale imprinted in the distribution of galaxies. This Baryan acoustic oscillation scale acts as a standard ruler etched across the cosmos. By measuring how this apparent ruler size changes with distance or redshift, surveys like the Sloan Digital Sky Survey can trace the expansion history of the universe, independently confirming the accelerated expansion and constraining dark energy's properties. The fourth pillar bends light itself. As light from distant galaxies travels to us, it is subtly distorted by the gravitational pull of all the matter, both visible and dark, in its path. This weak gravitational lensing creates a faint statistical warping of galaxy shapes. By mapping this cosmic shear across the sky, astronomers can reconstruct a three-dimensional mass map of the universe, directly probing how dark matter clumps and how that clumping has been suppressed over time by dark energy's repulsive push. These four pillars together form a cross-checked, ironclad case that something is causing cosmic acceleration. But to move from knowing it exists to understanding what it is, we need a new generation of cosmic cartographers. The future of this mystery lies with three revolutionary missions. The European Space Agency's Euclid telescope, now in space, is designed to create the largest, most precise three-dimensional map of the universe ever made. It will observe billions of galaxies, measuring both weak lensing and Baryan acoustic oscillations across 10 billion years of cosmic history. Its goal is to measure the equation of state of dark energy with unprecedented accuracy, determining if it truly is a constant or if it varies over time, a crucial test between the cosmological constant and dynamical models like quintessence. On the ground in Chile, the Vera C. Rubin Observatory's legacy survey of space and time will begin a decade-long cinematic scan of the southern sky. Its enormous mirror and giant camera will detect tens of billions of galaxies and millions of supernovae, creating a dynamic, living map of the cosmos. It will find rare, extreme objects that serve as natural laboratories, and its sheer statistical power will detect subtle deviations in the growth of structure that could reveal the fingerprints of modified gravity or interacting dark sectors. Then NASA's Nancy Grace Roman Space Telescope will join the hunt later this decade. With a field of view 100 times larger than the Hubble Space Telescope, Roman will conduct vast surveys for both supernova and weak lensing. It will precisely measure the distances to millions of galaxies, providing a high-definition movie of cosmic expansion. Crucially, Roman's infrared vision will peer back to the cosmic dawn, to the very epoch when dark energy is thought to have taken over, capturing the moment of transition in exquisite detail. Together, these observatories will not simply refine a number. They will perform a forensic investigation on the dark universe. Their data will strain theories to the breaking point. Can quintessence models match the detailed timeline of structure growth? Do the lensing maps show anomalies that point to emergent gravity or hidden dimensions? Does the equation of state waver, or does it stand rigid as a constant? Within the next decade, the elegant stories we have woven may face their most severe test as the universe's own evidence begins to rule possibilities out, forcing us closer to a truth that is undoubtedly stranger than any one theory alone. The data from future telescopes will be ruthless, and it must be. For all their elegance and ingenuity, every leading theory of dark energy carries profound, unresolved weaknesses. This healthy skepticism is not a sign of failure, but the engine of scientific progress, a rigorous process of stress testing ideas against reality. The cosmological constant, for all its observational success, is haunted by the fine-tuning problem. Its value must be set with impossible precision. If it were just slightly larger, even by 1 part in 100, the universe would have expanded so violently in its first moments that galaxies and stars could never have formed. If it were slightly smaller, the universe would have collapsed back on itself long before life arose. To produce a universe like ours, the initial conditions had to be balanced on a knife's edge of 1 part in 10 to the 120th power. This staggering level of fine-tuning feels deeply unsatisfying to many physicists. It suggests the constant is not explained by any deeper principle, but is simply a brute fact, a number written into the cosmos for no apparent reason. While the multiverse offers a philosophical escape, it does not erase the unease that our most successful model requires a numerical coincidence of cosmic proportions. Modified gravity theories like F of R or Mund face a different kind of trial, one of comprehensive consistency. Their great challenge is to seamlessly work across every scale of the universe. They must pass the stringent tests of our solar system with flying colors, matching the precise orbits of planets and the bending of starlight exactly as Einstein's theory does. Yet on galactic scales, they must diverge to explain rotation curves without dark matter, and on the largest cosmic scales, they must produce an accelerating expansion without dark energy. Crafting a single mathematical framework that accomplishes all three is like designing a single key that perfectly fits 3 radically different locks. So far, no modified gravity theory has achieved this trifecta. Many can explain 1 or 2 anomalies beautifully, but they stumble on the third. For instance, a theory that perfectly fits galaxy rotations might fail to reproduce the precise patterns of the cosmic microwave background or the observed gravitational lensing by massive galaxy clusters. The universe presents a unified set of data, and any theory that hopes to replace the dark universe must explain that full dataset, not just its most compelling pieces. Dynamic fields like quintessence offer a way out of the fine-tuning problem by making dark energy evolve, but they introduce their own mysteries. The most significant is the question of identity. In physics, fields are usually associated with fundamental particles. The electromagnetic field has the photon, the Higgs field has the Higgs boson. If quintessence is a real, dynamic field permeating the cosmos, where is its particle? What would a quantum of this fifth force be like? Theorists have proposed names like the quintessino, but no such particle appears in our current models, and there is no experimental hint of its existence. Furthermore, to behave as required, the quintessence field must be incredibly light and have an extremely flat potential, meaning it changes very slowly over cosmic time. This makes it susceptible to a host of quantum corrections that could easily destabilize it, reintroducing fine-tuning problems even more severe than the cosmological constants. In trying to solve one puzzle, quintessence often creates others, demanding new physics that is just as speculative as what it seeks to replace. The beauty of a dynamic solution is tempered by the reality that we have no evidence for the fundamental ingredient it requires. This rigorous criticism is not a dead end. It is a map of the battlefield showing where the current frontiers lie and where the next breakthroughs must occur. It forces cosmologists to be brutally honest, to follow the data even when it leads away from elegant ideas. The discomfort of these shortcomings is the very pressure that will either forge stronger theories or break the old ones, guiding us closer to a truth that for now remains hidden in the dark. The universe's accelerating end may have a startling echo in its explosive beginning. 14 billion years ago, in the first fraction of a second after the Big Bang, the cosmos underwent another, far more violent phase of runaway expansion called inflation. This epoch stretched a quantum speck to macroscopic size, smoothing and flattening the entire observable universe. Today, a much gentler acceleration, dark energy, is taking over. This mirroring poses a tantalizing question. Are these two bookends of cosmic history connected? Could the same underlying physics, perhaps even the same cosmic actor, be responsible for both the universe's birth throes and its final fate? This is the ambitious vision of Theory 28, the search for a deep interplay between inflation and dark energy. The symmetry is too compelling to ignore. Both phenomena involve a repulsive gravity, a period where the expansion of space accelerates dramatically. Inflation was driven by a hypothetical field called the inflaton, which temporarily locked the universe into a state of high vacuum energy, causing exponential growth. Dark energy, in many models, is driven by another field, like quintessence. The natural suspicion is that these two fields might be relatives, or perhaps even the same entity playing different roles at different times. This idea leads to a class of models with a beautifully unified name, quintessential inflation. The proposal is as elegant as it is grand. A single, rolling scalar field could have been responsible for everything. In the extreme energy of the first instant, this field would have been perched high on its potential energy slope, rolling slowly and driving the frantic expansion of inflation. As it rolled down, it would have eventually reached a steep drop, releasing its energy to reheat the universe, filling it with the hot plasma of the Big Bang. But then, instead of settling into a quiet minimum, the field would have entered a long, shallow plateau. For billions of years, it would have lain almost dormant, its energy density negligible compared to matter and radiation. Its presence would have been a cosmic sleeper, waiting as galaxies formed and stars ignited. Finally, as the universe expanded and thinned out, the field would have begun rolling again on this shallow plateau, its energy density now dominating the cosmos and acting as the quintessence that drives today's acceleration. The conceptual beauty is immense. It unifies the two most mysterious accelerations in cosmic history under one mathematical roof, using one fundamental ingredient. It tells a continuous story from the first trillionth of a second to the present day, with a single character evolving through the ages. It even offers a potential explanation for the staggering difference in energy scales. The vacuum energy during inflation was colossal, perhaps 120 orders of magnitude stronger than today's dark energy. In quintessential inflation, this is not a problem, it is the plot. The field simply rolls from a very high energy state to a very low one, its influence waxing and waning across the eons. The model paints the universe's expansion history as a single, coherent narrative arc, with a dramatic opening act, a long, complex middle, and a final chapter we are now beginning to read. Constructing a viable story, however, is a theoretical tightrope walk of astonishing difficulty. The challenges are profound. First, the field must reheat the universe efficiently after inflation, transferring its energy into the particles that become everything we see. If it rolls too quickly or gets trapped, the universe could end up cold and empty. Second, and more critically, is the long dormancy. The field must hide for over 10 billion years, its energy density remaining utterly insignificant while matter does all the work of building galaxies. This requires an incredibly flat plateau in the field's potential, a feature that must be exquisitely protected from quantum corrections that would naturally want to curve it. It is like balancing a marble on a perfectly level tabletop for the age of the universe, while subatomic vibrations constantly try to knock it off. Any tiny bump or dip could cause the field to roll too soon or in the wrong way, ruining the delicate timeline we observe. Finally, the model must end with the correct tiny acceleration we measure today, which requires the plateau to have just the right gentle slope. Getting all these pieces to align within a single, natural-looking mathematical potential is a Herculean task that has so far eluded a definitive, universally accepted solution. Yet the quest continues because the payoff would be a revelation. Finding evidence for such a unified model would mean that dark energy is not a late-coming anomaly. It is the final, fading echo of the very mechanism that created our universe, a cosmic breath held for billions of years before its final, gentle exhale. The force pushing galaxies apart today would be the oldest force in existence, a living relic from the first moment of time itself. Our most elegant equations might be mere approximations, glimpsing only the visible tip of a cosmic iceberg. The staggering fact that 95% of the universe is composed of entities we cannot see or touch is not just a scientific puzzle, it is a philosophical earthquake. It forces a profound and humbling reassessment of our place in the cosmos and the nature of reality itself. For centuries, humanity viewed the universe through an anthropocentric lens, believing the stuff of stars and planets, the matter we are made of, was the primary substance of creation. Dark matter and dark energy shatter that assumption completely. We are not the main characters in the cosmic story. We are a rare and fragile afterthought, a delicate froth on the surface of a deep, dark ocean whose currents we are only beginning to sense. This missing energy is a constant, quiet reminder that the universe was not built for us, and it operates by rules that extend far beyond the realm of our ordinary experience. It challenges the very premise of our investigation, suggesting that the physics we have perfected here on Earth, in our labs and our solar system, may be a local dialect in a much vaster and stranger cosmic language. The hunt for dark energy is not merely about finding a new particle or field. It is a search for a new grammar, a new set of principles that can describe a reality dominated by shadows. This situation is not without historical precedent. Think of the celestial spheres and complex epicycles of Ptolemaic astronomy. For over 1,000 years, astronomers added layer upon layer of intricate circles to their models to explain the wandering paths of planets against the fixed stars. The system worked, it made accurate predictions, but it was fundamentally wrong. A beautiful and convoluted fiction built upon a flawed assumption that Earth was the center of all motion. The truth revealed by Copernicus, Kepler, and Galileo was far simpler and far more profound, a heliocentric solar system governed by elegant mathematical laws. The dark universe today feels like a modern echo of those epicycles. We have our standard model of particle physics and general relativity, two magnificent predictive frameworks. Yet to make them fit the cosmos, we are forced to add two enormous, unexplained components, dark matter and dark energy, comprising almost everything. Could these be our contemporary epicycles, elaborate fixes clinging to a framework that is incomplete? Are we waiting for our own Copernican revolution, a shift in perspective so radical that the darkness simply dissolves into a new, clearer light? Another powerful analogy is the luminiferous ether. In the 19th century, physicists were convinced that light waves, like sound waves, needed a medium to travel through. They postulated an invisible, frictionless substance permeating all of space, the ether. Decades of ingenious experiments, most famously by Michelson and Morley, failed to detect its influence. This negative result was not a failure, it was a guidepost. It forced Einstein to abandon the ether entirely and build his theory of special relativity on the constancy of the speed of light in a vacuum. The ether was not a thing to be found, it was a conceptual crutch that needed to be kicked away for a deeper truth to emerge. Today, we pour immense resources into searching for WIMP, actions, and other candidates for the dark sector. What if, like the ether, dark matter and dark energy are not things to be found, but signs that our concepts of gravity, space-time, or mass are in need of a similarly revolutionary overhaul? The philosophical weight of this possibility is immense. It means we are not just filling in blanks on a mostly complete map. We may be realizing that the map we have is of a single continent, while an entire unseen world lies across the ocean. Every null result from a deep underground detector, every theoretical tension, is not a setback, but a clue pointing toward a paradigm shift as profound as the advent of relativity or quantum mechanics. Those revolutions taught us that space and time are relative and that particles behave as waves. The next revolution may teach us that what we call empty space is the source of cosmic fate, and that the mass we see is a minor perturbation in a universe built from information or entanglement. To solve the mystery of missing energy, we may need to surrender not just our equations, but our deepest intuitions about what is real. Perhaps the final theory is not about what dark energy is, but about how we will finally see it. The next great leap in this cosmic mystery may not come from a lone genius with a chalkboard, but from the silent, relentless calculations of machines. As our telescopes gather torrents of data, we are turning to our most powerful tools to sift through the noise, building virtual universes to test our wildest ideas. Supercomputer simulations have become the ultimate cosmic laboratories. Since we cannot rerun the universe with different settings, we must build digital twins. Scientists start with the initial conditions of the Big Bang, encoded in the cosmic microwave background. They then program in the laws of physics as we understand them, including a specific candidate for dark energy, be it a cosmological constant, a quintessence field, or a modification to gravity. They add a prescription for dark matter, whether it is cold, warm, or made of sterile neutrinos. Then they set the simulation in motion, watching as billions of years of cosmic evolution unfold over weeks or months inside a supercomputer's memory. These are not simple animations. They are staggeringly complex n-body simulations that track the gravitational dance of trillions of particles, each representing a clump of dark matter. They model the hydrodynamics of gas, the formation of stars, the feedback from supernova and black holes. The goal is to see which simulated universe, built from which theoretical ingredients, grows to look exactly like the one we see outside our window. Does the distribution of galaxies in the virtual sky match the intricate cosmic web observed by the Sloan Digital Sky Survey? Do the virtual galaxy clusters have the right mass, shape, and internal dynamics? Does the simulated history of cosmic expansion precisely trace the curve we measure from supernova? By running thousands of these simulations with slightly different parameters, cosmologists can perform a kind of cosmic fingerprint matching, seeing which theoretical fingerprint leaves a mark that aligns with reality. This process has already ruled out many simple models, but the data flood is becoming a deluge. The Vera-C, Rubin Observatory's legacy survey of space and time, will not just provide a map, it will provide a 10-year-long movie of the sky, generating hundreds of petabytes of data. Within this ocean of light, the subtle signatures of the true dark energy may be hidden in patterns too complex for any human to discern. This is where a new partner enters the search: artificial intelligence. Machine learning algorithms are being trained to find the needles in these cosmic haystacks. Unlike traditional analysis, which often looks for specific, predicted signals, AI can be set loose to find anomalies, correlations, or structures that no theorist ever thought to look for. Imagine an AI system trained on millions of simulated universes, each with a different dark energy model. It learns the unique statistical imprint that each model leaves on the large-scale structure of the cosmos, the specific way it arranges galaxies and voids. Then we feed it the real, observed data. The AI does not just compare, it hunts. It might discover that the real universe's structure has a faint but consistent statistical quirk that only matches one type of quintessence field, or that the shapes of distant galaxies are distorted in a way that points directly to a specific modification of gravity. More thrillingly, it might find a pattern that matches none of our simulations, a signature of something entirely new, a theory we have not yet conceived. This is not science fiction. Teams are already using these techniques to scour existing data, and the next generation of surveys will be designed with an AI-driven discovery in mind. The solution to the universe's greatest mystery may therefore emerge from a collaboration between human curiosity and machine perception. We will pose the questions, build the virtual worlds, and point the telescopes. The machines will sift the starlight, find the hidden patterns, and whisper back a clue we might have missed. In the end, the key to the dark may be written in a language of data so vast that only by teaching our creations to see in the dark can we hope to find it ourselves. From a single mathematical fudge factor to holographic projections and gravity that emerges from cosmic information, we have wandered through a landscape of breathtaking imagination. This is not a sign of confusion, but of a science vibrantly alive, confronting its greatest enigma. The missing energy of the universe represents more than a gap in our accounting. It is a fundamental crack in the foundation of our understanding, a silent question that echoes across every galaxy. Whether the answer lies in a forgotten field, a rewritten law of gravity, or a reality far stranger than we dare to suppose, one truth is inescapable. Solving this mystery will not merely fill in a blank on a chart. It will force a revolution in physics as profound as those wrought by Newton and Einstein, reshaping our conception of reality from the quantum vacuum to the cosmic horizon. The next decade promises a flood of data from telescopes like Euclid, Rubin, and Roman, data that will strain these elegant theories to their breaking points. We stand on the precipice of discovery, so we turn the question to you. After this journey through 30 possibilities, which theory resonates most deeply? Does the simplicity of the cosmological constant appeal to you, or does the dynamic story of quintessence feel more true? Perhaps the holographic principle or emergent gravity sparks your sense of wonder. Share your thoughts in the comments below. This conversation is just beginning. If you crave more deep dives into the universe's grandest puzzles, be sure to subscribe. The greatest story ever told is still being written, and its next chapter, hidden in the dark, is waiting to be revealed.